So starting beautiful slideshow. Yep. All right, welcome everyone to our intro to graphs for beginners workshop. How are you? Huh? I'm Stetten Festler, the committee chair for the DSA club. This is Phuc Truong, our president. So how comfortable is everyone with graphs? And get like a thumbs up if easy peasy, thumbs down, very bad, like in the middle. Okay, not bad, not bad. So we'll go over some quick definitions. I'm sure most of you are probably familiar with these, but we have the vertex. So in this particular graph, A, B, C, and D are considered vertices, also known as nodes. And then we have the edges between nodes, which are connections between nodes. So we can, from A, we can visit B because there is an edge here. And then, and this graph is unweighted, but edges can have weights associated with them. So let's say this edge had a weight of 10. So in order to go from A to B, we would have to pay or take into consideration that there is a weight associated with that edge.
You can hide it. You click on more. You can hide it. The hide floating we can control.
There we go. That's better. Okay. Now for some types of graphs. So you can see that this is a directed graph where edges can only flow in one direction. So what that means is from B, we can visit A, but from A, we cannot visit B because this edge only flows in one direction. And then in an undirected graph, edges are bidirectional, meaning from B, we can visit A, and from A, we can also visit B.
So real quick, so what type of like real world application can you see being used with directed graph? Hello, welcome in.
Hello.
Are you for the club meeting? Sweet, welcome. We have donuts over there.
Yeah.
Yeah, so real quick, like say, so undirected graph, what do you think is like one real world application that like can be represented with that, with undirected graph?
Another question?
Yeah.
Nothing. Nothing maybe?
Oh, yeah, like roads.
Sure.
Okay, yeah. Or city, right? Google Map, like the nodes could be like the city, and then the edges could be like the map that can, the path that connects with that. And then for a directed graph, maybe something more specific that needs like only one directional. Yeah, so I was thinking like maybe something like Pokemon type matching. Like you have like fire, water, grass, and then what fire is weak to water, so you'd be like an arrow, and then go from there. So just something I thought of.
So essentially you have to be a Pokemon nerd in order to understand graphs.
Yeah.
Otherwise.
Unless you can run like a cycle detection on that graph to find like the three type matchup for a starter. Anyway, continue.
All right.
Okay.
All right, then we have acyclic and cyclic graphs. So in an acyclic graph or in a cyclic graph, at least one node can be traced back to itself. So we say if we start at A here, we can go from A to C to B, and then we can revisit A. So that's considered a cycle. Whereas in this graph, you can never visit a node more than once. So it's acyclic. Any questions so far? All feeling good? Nice. And then we're going to go over some graph representations. So for edge lists, I don't see these very often, but I guess it's good to know how they work and just understand them. So in an edge list, we have an array, and each element in this array is a tuple, and this represents an edge. So from A, there is an edge, a directed edge to B. And then this represents an edge from A to C. So we see from A, there's a directed edge to C. And from B to C, there's also a directed edge. So from B, we have a directed edge to C. Does that make sense?
You said you don't come across this very often. What are some of the use cases you come across in the graphs?
So usually adjacency lists are what I most often see graphs represented as. Yeah, I would think that's the most important for me so far.
So there are like three different ways that you can like represent a graph when it comes to coding. What he just went over was what was the previous one?
Was
Edge list. Yeah, it's just literally just like a list of edges, and then the next one is adjacency list.
Yeah,
This is like the most common one that most people gonna use.
yeah,
Mostly code problem gonna use this.
99% of the time.
Yeah,
I'd say.
99% of the time. And then the last one is matrix, adjacency matrix. This is only really used for when you have the graph is really dense. That means there's a lot of edges. So you have like a combination of every single node. So using that is going to be more efficient. This is not really very common anyway. So yeah, so if you want to go back to the
Yeah,
previous
let's-
slide, this is like the most important one.
Let's go back and explain this. So for an adjacency list, we usually use a dictionary or a hash set. You could call it in other languages. And so the keys in here are the nodes in the graph. So we have key A represents node A. And then the value is a list of the nodes that that are children of this node or that this node points to. So A points to B, we can see there's an edge there, and A also has an edge to C. So we see that edge right there. Yeah. Adjacency lists. And for adjacency matrices, these aren't as common, but also good to know. So it's usually a 2D array representing this. So matrix ij is true if there exists an edge from vertex I to vertex j. So we see here at node 0, we'll go to node 0's row. We see that there's a 1 in column 1, which means that there is an edge from 0 to 1. Also in row 0, there's a 1 in column 2, meaning that we have an edge from 0 to 2. And yeah.
Yeah, it's just like a table of combination of different nodes to see if there's an edge or not.
Being used in conflict mapping. That would be if you were using a graph to represent like traversal paths, like, but on a massive level, you said like this is often used if there's just a massive amount.
Yeah, it'd be really dense because otherwise you're just using a ton of space and yeah, for no reason. Yeah, exactly. Yeah. And you'll take over.
Sure. Yeah, so when it comes to graph traversal, the most popular ones are DFS and BFS. So I assume most of you are familiar with DFS or BFS, or how to. Okay, yeah, it's fine. I'll go really in depth into it. So DFS is a depth first search, and it will start at some root node, explore path as far as it can, and then backtrack. Don't worry if it doesn't make sense right now. I will go like visual on it. And then breadth first search is going all nodes at the current depth, all level by level. BFS is useful for finding shortest path to a vertex. So for example, I have a graph right here. Okay, so I drew out this graph. It's a directional graph. It has 10 nodes labeled from 0 to 9, and here are the different edges. So when it comes to, if like say right now, if I want to traverse the graph starting from node 0, there's two options. I could do DFS or BFS. So the way DFS works is it's going to go through. So okay, so from 0, there are 4 possible paths, right? It can either 0 go to 1, 0 go to 2, 0 go to 5, 0 go to 4. So DFS is going to go through them one by one. It's going to go to 0 to 1 first. So 1 doesn't have any return. Now it's going to go to 0 to 2, and then 0 from 2. What possible path is there from 2 to go to? Yeah, to 3. And from 3, it has 2 options: go to 7 or 9. So it's going to go to 7 first, and then 7 it terminates. Then go back to 3, and then from 3 it goes to 9, and then it go back, and then so it finished all the possible path for 3. It backtrack backtrack back to 0. So from 0, 1 is done, 2 is done, the next one is 5, it goes to 5, from 5 goes to 8, then just go back, and from 0 here, so 1, 2, and 5 are done, it goes down to 4, so 0, 4, and 6, and finish. So it finished, it go through all the nodes in the graph once, in the order.
Seems to be like super similar to how trees work.
Yep, exactly. Yeah. So that's why I said earlier, graph is like an extension of tree. But okay, here's the tricky part though. So you notice how this graph, I purposely made it looks like a tree, but in normal graph, it could have like a node that goes from 3 to 5. So what if that is the case? So how would the DFS looks like? So remember, so Xcode draw, yeah, Xcode draw. 7, 9, 5, 8, 4, 6. So that's the order that it goes when there's no edge from 3 to 5, right? But what if there is an edge from 3 to 5? What would it looks like? Starting from 0.
2, 3, and then 7, 9, and 5, and 8.
So it's gonna go 0, and then it goes to 1. Then 2, okay. Then 3. Okay, now here's the tricky part. So from 3, what possible path does it have? Yeah, so 7 or 9 or 5. So let's go to 7 first. Take care of 7. Go to 9. Okay, 5. Yep. 5 and then go to 8. Yep.
So the 5 branches of the cursive would be settled.
Mhm.
3 and then the 2 then to 0. Then would it go 5, 8 after that?
So okay, so it finished 8, right? So it backtracks, go back to 5, 4, back to 0. So from 0, it's done with 1, it's done with 2. Now it's going to go to 5. But is it actually going to go to 5 again?
Do most graphs get designed such that it keeps track of what's been visited so far?
Yep.
No.
There's going to be like a visited set, so that it knows that 5 has already been visited. So it's going to try to go to 5, but then it's like, oh wait, actually 5 is already visited, so it's not going to go to. So it's going to go back to 0, then 4 and 6.
Short circuits.
Yep. Yeah, so that's DFS. So basically DFS is like going path by path, like all. So it has like a list of possible choices that goes one by one. Yeah.
So what if there's like a cycle in the graph?
Yep. Okay.
Do we ignore that, or like, is it because we have a visited set and we keep track of it?
Yeah, let's make a cycle and see what happened. So 3, 2, 3, 5. So let's make 5 connected to, yeah, to make it a cycle. So there's a cycle right there, right? 2, 3, 5. So starting from 0, it goes to yeah, DFS with cycle. Okay. So good one. Hello, welcome in. You Tada?
Yeah.
Oh, nice to meet you. Web donuts over there. 0, 1, goes to 2, goes to 3, go to 7, go to 9, go to 5. Okay, so now from 5, we have two. What option do we have from 5 to go to? 2 and 8, yeah. So it's from 5, it's going to attempt to go back to 2, but 2 is already visited, so it's not going to. So it's just going to go straight to 8. And then backtrack. So yeah, 0. So it's just 4 and 6. Does that make sense so far? Yeah, not really. So this is just DFS, and I will prove that by. I actually wrote down the DFS code right here. So right here. So this is what the code looks like. So this is our input. So 10 signify how many nodes there are. And here are the list of edges. And then, so that's what it takes in as the input. And the first thing it does is that it create remember what we said earlier about building adjacency list. So this is what this code is doing right here. It's building a graph, and in that graph, it's going to have the key is going to be the node, and the value is going to be the edges that it connects to. And then this is the code for DFS. So we check, the first thing we do is we check if the node is invisited. If it is, then it terminates. If not, then we add it into a set of visited. So yeah, you're right. We have like a visited set right here. And then, so what this part does is right here is it checking for all the possible neighbors, and then it perform DFS again on that neighbor. So remember, like in here, 0, all the possible neighbor are 1, 2, 5, and 4. That's what this is doing right here. For neighbor in graph of node, which is 0 for possible path. If it's not visited, then it's going to do DFS on it. So when I click on run, you're going to see it. So this is the graph that we have. So 0 is connect to 1, 2, 5, 4. As you can see here, 0, 1, 2, 5, 4. 2 connect to 3. 2 connect to 3. You can see it though, right? It makes sense, right? The graph. And then 5 connect to 8. 5 is connect to 8. And then when it print out all the nodes that it visited in order, as you can see, it's go from 0, 1, 2, 3. It's hard to see.
Weird random side. Back in the code, it adds it to visited. Does that? It doesn't just flip a flag. Just seems expensive. Does that you have to run through the collection of visited for each traversal? I remember this.
Well, the thing is, like, visited is a set, and when you look up something on a set, the runtime is O of 1. It's not going to be ON. Yeah, yeah, I was surprised to learn that too. But the thing is, in Python, look up time of a set in Python. Yeah, it's anyway, it's O1, so it's not expensive.
That's really cool.
Yeah, I when I first found out about that, it's pretty surprising for me too. So as you can see here, it printed out in order correctly, right? So 0, 1, 2, 3, 7, 9, 5, 8, 4, 6. Okay, now let's try to add a new node. Let's add 3 to 5 actually. Forgot to add 3 to 5. So I'm gonna add a new edge in here. 3 to 5, so 5, 3.
See everybody.
So see how it changes. 0, 1, 2, 3, 7, 9, 5, 8, and then 4, 6. See how it reflects the changes in the code. Yep. So that's DFS. Any questions? Does that make sense? Yeah.
So why do you prefer DFS over DFS? So when do you actually want to use DFS on DFS?
Yeah. I will go. I haven't gone over DFS yet. I'm going to go to it. Right? Yeah. So that's DFS for you. And then slide. So yeah, so DFS. That's the code. This is honestly something that you should be able to like code during like a coding interview. You should just like memorize this. I will post a slide later so you can like see the code. I would put this like in your note or something. This is like something, this is like a template, something you just like use over and over. So that's DFS. Okay, so back to BFS. BFS. Drawing. Okay, so let's just use the same graph. So BFS is going to be level order traversal. So in DFS, all the possible path was like 1, 2, 5, 4, and it's finished one of them one by one, right? Each of them one by one. However, in BFS, it's going to do all of them at the same time. So it's going to start from 0. BFS. So starting from 0, so all the possible nodes of 0 is going to be 1, 2, 5, 4. So it's going to visit those first. So 1, 2, 5, 4. Okay, So from 1, 2, 5, 4. From 2, it can go to 3, right? And from 5, it can go to 8. From 4, it can go to 6. So 3, 8, 6 is going to be the next level. So 3, 8, 6. It's going to be the next level. Okay, so now we're at 3, 8, 6. Then the next one is going to be 7 and 9. 7 and 9. So it's literally just going level by level. And it's different from DFS. DFS is going one by one of the neighbor. BFS is going all of them at the same time. So yeah, I can show you. So does that make sense though so far? Okay. So the way you do that in code. We're actually going to use a queue. There's a lot of way, but the most popular one is using a queue. Let's see where we're okay. So I actually did not code it, so I guess we could just do it real quick.
So it's reading children, loading it into a queue, and then unloading the queue kind of thing.
Yes. Yeah. So for when it comes to BFS, what you want to use is a queue. So define BFS. Text in the node. So you always want to start a queue. So in Python, it's called DQ. And maybe you want to have like a level as well to see what level we're at. Do like a while loop while queue exists. We get the length of the queue. So size equals length of queue. For I in range of size. This is we're just popping out the elements. So node equals queue dot pop left.
Wouldn't you want to insert a node in the queue first, or do you go into the while loop? Because right now the queue is empty.
Right. Yeah. So we have to put something in the queue first. Yeah. Queue dot append node for neighbor in a graph of node. Actually, call it current node. So for every single neighbor, we add it to the queue. Queue dot append neighbor. Let's see. Oh, okay. Yeah. Yeah. Thanks for coming though. Then queue dot append neighbor.
You're looking at the neighbors of the current node, right?
Yes. For in range. And the level plus equals from. What is it?
Yeah, where are you getting graph from undefined?
Oh, it's gonna be up here. The same here. Yeah, I'm gonna paste it in later. So let's go back. Kind of forgot, honestly. Okay, so we do have a visited set as well. Yeah. Yeah, we have to keep track of what node has been visited or not. So If neighbor not in visited, then we add it into the queue. Level +1. I think that's all we have to do.
Then you also add it to the set too.
Right. Yeah, you're right. No, we do it. Okay. As soon as we pop it, we can just add it into visited. Okay, wait. Yeah, that should do it. And then, yeah, I think this looks good. Yeah. Paste it in here. So we have access to graph. Jeez.
Then another.
Oh, okay, almost there. Okay.
Or.
On what line? Okay. That looks good. Think so. Okay, well then I will comment this out. Well, Um. Oh yeah, we don't need to add it there. BFS here. Okay. Then when I click on run, let's see what happens. Oh, I didn't print it. It's good. Okay, let's see if it works. So. Let's see. Okay, so start from 0, it goes to 1, 2, 5, 4, 3, 8, 6, 7, 9. Look at that, it works. So let's add a new edge in it just to see what happened. Actually, any questions so far though? On that. So I know if the code doesn't make sense. Yeah.
So I noticed that like, for BFS, you're doing it, iteratively, right? Is there a
Yes.
way to do it recursively or?
You would have to pass in the queue to each function. So it's a little bit messy.
Huh. I actually never done iterative.
Because I know
BFS.
BFS, you could do it both.
Yeah, yeah.
But BFS. or-
Honestly, like any recursion, you can do iteratively. Yeah, I think so. Yeah. So the way the code works, something you just probably just need to analyze more. But this is like the template. You should like memorize it. When it comes to solving BFS problems. And so let's see right now. Let's see if we add another edge. Let's say there's going to be an edge from 3 to 5. Would it change anything? And then another one from 8 to 4. So 8 to 4. So 4, 8, and 5. So it doesn't change. It makes sense because it's just traveling level by level. So back to your question. So when do you guys think we use BFS over DFS? When is it useful to go level by level? Let's say from 0 to 7,
I think you mentioned.
0 to 6, yeah.
You wanted to find the shortest path, right? I think that first search is more used for like, if you're trying to find something. Right? Like,
Yeah.
Like, cause you're going deep in, farther out.
Yeah. So, yep, just, so the way it works, because BFS is running, level by level, it's always gonna warranty, if we keep track of like how many levels that it went through, then we know that's the shortest path from one node to another. So from 0 to 8, the shortest path is 0, 5, 8. And because it travel level by level, we know for the fact that it's gonna go, the shortest path is gonna be 2. So I found a really cool website that visualizes it right here. We'll show it right now. You guys, yeah, it's gonna be like really cool. Okay, this right here, it's like ridiculous. So here you can like visualize DFS and BFS. So let's run BFS first. So this is the starting position. This is the end. When you click on it,
Whoa.
so do you see what just happened? From this point, you can think of the grid as like a graph, and every grid is like a node, and the edges is like top, right, left, and bottom. So it's starting from here. You guys see how it like spread out like a circle? That's BFS is running level by level. So from this point, it can either go up, left, right, or down. Let's try again. Yeah, you can see it like going level by level. So it reached there, that's the shortest path. Clear board. So here the cool part. So I can draw a wall here. So that means the straight line is no longer the shortest path. Like that. Okay. It's like kind of glitchy.
Never really thought of, how to find it.
Like that. So yeah, so BFS you can see it's like level by level. Shortest path. So let's see what DFS looks like. So what do you guys think DFS gonna look like?
Yeah, take a long time.
Yeah.
Like this.
Yeah, it's gonna. Yeah. So it's going to go. So from here, remember it has 4 options, right? So BFS is going to do all 4 at the same time, but DFS is going to pick one and commit to it. So it's going to go top, then top from top, keep on going top, up here no more. The option is left to right, so left and right. Here, I'm going to shut up and show you. Yeah. It's so freaking cool. I love this. Honestly, like if anybody like want to like recreate this website, like using React or anything, would look amazing. Resume talking about you.
Can we look at the algorithm?
Yeah. Honestly, I don't know the difference between Dijkstra and BFS. It looked just like BFS to me. And then A star.
I see A star a lot.
Whoa.
Like Pathfinder algorithms.
Oh, actually, I think A star is like a mix of greedy and BFS. Yeah, I learned it in CSC 140. It's been a long time ago. Yeah, let's get back here. So when it comes to time complexity, well, if you start from the graph here, all of them, both DFS and BFS gonna traverse each node once. So it's gonna be ON for space complexity. You just traversing through all the node at least once. For space, because we keep track of a visited set, it's also gonna be ON. Yeah, for both. Let's see what else. So I have example problem here. If you got, yeah, I guess we could try. And any question though? How do you guys feel? Hard, easy, medium? Don't worry if you like don't get it right now. It took me a long time to get all of this stuff. So just keep practicing and like posting question on Discord and just
You have the code on Discord, the slides.
the slide. I can send the link. I can put it into the link later. Yeah, don't feel bad if you like don't get it right now. It's just something you gotta practice.
This is an intro.
Huh?
This is an intro.
Well, I mean. Okay.
So this problem is graph. You know, it's using a 2D matrix instead of hopefully looking at for.
Yeah, so this is different. It's using a grid instead of the adjacency list. So it's a little bit different. Yeah. So the problem is given n by n to the binary grid, represent a map of 1 and 0. So 1 is land, 0 is water, return the number of islands. So for example, right here, the number of island is going to be 1. Because you can see there's like 1 connected island in here. Here, the number of islands is 3. So there's 1 right here. That's 1 island. That's 1 island. It's not connected to anything else. 1 and 1 here is 1 island. It's just only connected to itself. Does that make sense? Let me check Zoom real quick. Wait, what? Did it stop? No, huh. What happened to Zoom? Okay. So you guys got the problem, or I can try it.
It's been a while.
Yeah, so like you have a grid. 5.
What an idea. I think like just iterate over all like the cells in the matrix, right? And then if you encounter land, you just run DFS until there's no more like land.
Yeah, so the first one is 1, so that's an island, 1, 1. So that's water, 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 empty. 1, 1. 1. So an island is like connected land.
Yeah.
So these 4 are connected, right? This is connected, this is connected. So the total number of island is going to be 3. So we have that kind of input. They're asking, how do we figure out how many islands there are in this grid?
Oh, I have a question.
Yeah.
So like, so since this is a different type of graph, how do you keep track of like the cell that you've already visited?
You could just use a visited set. So you could have like a visited set. And then when you visit a cell, it's going to be in the form of row and column. So 1, 2, 3, 4, 0, 1, 2, 3. So this is cell 0, 1. So when you add here, you just add it into the set. That's how you can track. So
I had a different idea.
how do you think?
2D Boolean.
2D Boolean?
Yeah. So all of them are set to false, and for each one you visit, you set to true.
You know what? That could actually work.
Yeah.
Yeah. Yeah.
That might be even easier if you were asked this, maybe you'd ask first, but you said, since like you're given a 2D array, once you visit it, you just set it to 0.
Oh, yeah, yeah, that's, yeah.
That would be the final optimization. So we're just starting, so I think we'll go with the set, and then finally, fully optimized will be the in place.
Yeah, for sure. So I think we should stick with this, just so like it's easier to understand than like setting it to 0. So so the idea is like you just run your DFS on every single cell. So starting from 0, 0, if you run DFS, or BFS, it doesn't matter, because when you run it, it's gonna visit all the possible nodes that connected to it anyway. So from here, if you run DFS, you're going to get all the cells that connected to it. So from here, 0 to 0, when you run DFS, you're gonna have 0, 0, 0, 1, 1, 0, 1, 1. You're gonna add it into the visited set, and then you go to the next one, and then you increase the count. You increase the count, number count, island count by 1 after you do DFS. And then you move to the next one, and from here you have to run DFS again. But we know that this is already visited, so we know that we already counted it, so we don't have to run DFS. From here, it's a 0. We don't do anything because it's just water. Same here. If we run DFS again, it's already visited, so it doesn't do anything. So the count doesn't increase. Here again, if we run DFS, it's already visited. Don't do it. But then we go here. This cell is not already visited, so it's going to run DFS on it, which is going to cover this part. So we increase the count by 1 again, and then now count is going to be 2, and then keep doing until we reach here. We run it again, and it increase by 1 again. So that's a general technique on how to solve it. This problem you can solve with both DFS or BFS, doesn't matter. So I'll just do it real quick. DFS.
Yeah, so like, how would you visit the neighboring cells in the matrix?
Yeah, that's a good one.
That's one question.
Rows. So the first thing we do is like we count how many rows and columns there are to make it easier to calculate. You're heading up?
Yeah, I have a class to get to.
Okay, sounds good. Yeah, thanks for coming.
Of course, yeah.
We'll do more events next time.
Yeah, of course.
Yeah.
I thought like we covered the shortest the part. So topological sorting was added today, right?
Yeah, we could do it next time too.
Yeah, of course, yeah. It's already time for class at 3:30.
Okay.
Yeah, great.
Yeah.
Thank you so much.
Yep.
Bye, guys.
Number of rows is going to be length of grid. Row cost equals length of grid of 0. So these are just like to get the size of the grid. So rows on this case is like how many rows there are. So which is going to be four rows, and then column is like how many columns there are, which is five columns. And then we have a visited set. Okay, so DFS is going to take in the row and column, which is like the index of where we're at. And then from here, we can check. I like to define like a directions. This is like what I normally do. So directions for DRDC in directions. Goes R plus D or C plus DC. So these are new row. Call it new. New row.
Like, can you iterate like that?
Yeah.
RDC.
Yeah. So the RDC is just like 0, 1, 0, -1. It will make sense. It doesn't make sense right now, but I will explain it. And then we check if new row in range of rows. And new column in range of columns. And new row, new not in visited. So this is just like to check, and then what else do we need to see? And new row, new call.
Wouldn't you also need to check like if you're within the balance of the grid as well?
Yeah, that's what this line are doing.
Okay.
New rows, like, and make sure it's in range. That's what they're doing right there.
That's a.
Yeah. I don't think it's very efficient though, like if you, right?
Yeah.
Probably might be a little bit more visual, to separate that for function. See if it's not within balance and it's not.
Yeah. And what else do we need to check on the new position? It's not visited, it's not out of bounds. Yeah. So it has to be one, right? If it's 0, then we don't run DFS on it. That's the case, then we run DFS on it. Row new call.
Then you need to. You need a sort of counter.
Yeah. Actually, the first thing we do though, is to add it into visited. Oh, no, okay, have to add make sure. So visited add. Anything else I need to do here? Oh, you're right, yeah. Nice. Okay, so that's the function for DFS. And or the thing is, like, we have to call it for every single cell. So for our in range of rows. We just call it DFS. Well, actually, if R and C not invisible, DFS R and C, and we increase the counts or results plus equals 1. And at the end we return result.
Also check it, starting with this.
1 second. So it's say that again.
So I'd like to just check.
Or
You wouldn't start and give us line.
oh, that's true. Yeah, yeah. And grid or and C equals. Okay. And everything looks good or anything else? I think it looks good. All right, let's run it. New row. Oh. Okay. Submit. So that runtime is horrendous. Let's see if we can optimize it. So you mentioned something about setting it to 0 instead of using visited. So let's do that. So instead of visited.add, we set it to 0. So grid of R and C equals 0. And then down here, we don't need to check with this.
Phuc, I think that's the one. Equals.
Oh, yeah. So we don't need to check for that anymore. And it has to be equals to 1. If grid. So we don't need to do this.
Are you sure about mixing matching is like, that's an integer 0, with string 2.
Oh, yeah.
Yeah.
Yeah, right.
And actually probably would be faster. Less memory.
Yeah, so we can see a jump from memory. So last time we used 22 megabyte. Now we don't use the set. It reduced down to 16.5. However, that runtime is horrendous. Any way we can fix this? It shouldn't, right? Because you're visiting every cell once.
Well, conversion usually slower.
Right.
Okay.
Okay. Well, I mean, like as far as like interview go for new grad, I think this is good. Questions? Sorry, I kind of ramble. I could explain this again if you guys need it. You got it? You feel good?
Yeah.
Cool. So yeah, I kind of want to get into topological sort, but maybe next time. I didn't prepare a slide. But...
You're gonna do a Python, right?
Huh?
You gonna do Python for the meetings?
Python, yeah. How do you guys feel about the workshop?
Sounds good.
Was it good? Cool. Yeah, great. Any feedback, comments? What do you guys want to do next time?
I think maybe spend a little less time on the code.
Oh, really? Okay.
Yeah, I think it's way better if you just like write it out and just like, leave it up to us to code it ourselves.
Okay. So like just pseudocode something.
Yeah, pseudocode or just draw it on the board.
Okay.
Just
Yeah.
explain like, the whole process of like, how would you
Yeah.
approach the problem.
Do you guys want to like do weekly problem on Discord? Like, so I post like a set of questions and then we work on it. You guys can work on it, and then next time we meet again, we can like discuss the solutions. Or you guys want to do that? That's what we did at the beginning,
Yeah.
but then nobody does it, so I kind of stopped. Yeah. We could do that, right?
Yeah, I'd be,
Okay.
if it's just like one problem.
Okay, yeah, we could do that. So next events, what do you guys want to do? So I have a few ideas. We could do Kahoot, game night, or another workshop, or another blitz.